Hello everyone, in this video we are going to learn how we can build a decision tree using R. So we are going to use a data set from a bank. The bank manager of a bank wants to use historical data from 500 bank customers to develop a classification model for determining whether or not new bank customers will respond to a HELOC offer. The manager also thinks that the bank is not targeting the right customers when marketing its HELOC products and hopes that the classification model will offer actionable insights for this company. The manager plans to assess the performance of the model and then classify 20 new bank customers as likely or unlikely to respond to a HELOC offer. Now we are going to use R to build preferred classification tree and then use this tree to score the new cases. First, we need to open our dataset and import the dataset to R. But before that, make sure you set your working directory to the working directory that your dataset is in, and then open. And after that, type my data is equal to read.csv, and in the parentheses and in quotation mark, the name or title of the document, which in this case I have helloc.csv, and then Control Enter. Once you import the data, you will see under Environment pane the dataset. In this dataset we have 500 observations and 4 variables. We can quickly check the dataset. Here on the screen you see the dataset. As you see, the dataset is composed of 4 variables: age, sex, income, and whether the customer responds to HELOC offer or not. So we will use this dataset to build a decision tree, and finally we are going to score new customers. So we need some packages to do these tasks. Therefore, you need to install caret, gains, rpart, rpart.pilot, proc packages. And after you install them, in order to activate these packages, you need to type library caret and library for each packages that we are going to use. Since I have already installed these packages, I'm going to make them inactive because I don't need to reinstall these packages again. For constructing a classification tree model, R requires that the target variable, HELOC, be a factor variable. So therefore, we are going to use s.factor command to convert HELOC variable into a categorical variable. Therefore, we are going to first choose the HELOC variable from my dataset and then equals s.factor and again my data and choose the parameter HELOC and then Control Enter. So now you have HELOC, which is our target variable, is a categorical variable and is saved as a factor variable in R. We use the set.seed command to set the random seed to 1. Therefore, we will generate the same partitions in each time we run the code. And then we use the create data partition function to partition the data into training, which is composed of 70% of dataset, and then validation, which is composed of 30% of the dataset. So let's first enter set.seed, which is 1, and then Control Enter in order to get the same results every time we run the code. And then we are going to create a new object called myIndex is equal to create data partition, and then open the parentheses, my data, and take the HELOC from my data. We don't need parentheses here. And then comma, p is equal to 0.7 because the partition we want is 70 to 30, and then list is equal to false. And now we are going to Control Enter. So we created my index, and this is composed of 70% of the data. Now let's call train set is equal to my data, and then we are going to get my index from my data and then Control Enter. So we created a train set which composed of 350 observations and 4 variables, and the remaining is going to be validation set is equal to my data in the parentheses negative my index because we want everything else than my index, and then comma, and then Control Enter. So we have of 150 observations for variables in the validation set. We use the rpart function to generate the default classification tree, which is going to be our default underscore tree. Within the rpart function, we specify the model structure, data source, and method. The method option is set to class, which represents a classification tree. To view the details about the default tree, we use the summary function. Because R uses the cross-validation method for pruning the tree, to ensure consistency of cross-validation results, again we use the set.seed1 function. So first let's enter set.seed1 and then control enter. And next we are going to create our default tree, which is called default underscore tree, is equal to, rpart function is going to do that for us. Hello is our target variable, and the remaining variables are going to be our predictors, comma, data we need to determine which data set we will use, which is train set, and then comma, method is going to be classification tree, therefore it is class, and then close the parentheses, and then control enter. Now we created our default tree, and to get the summary we use the summary function, and in summary we are going to determine the tree, which is default tree, and then control enter. So you can see the results on the console pane, but which is not very user friendly, the results. Therefore, to view the classification tree visually, we use the PRP function. The type option is set equal to 1 so that all nodes except the leaf nodes are labeled in the tree diagram. The extra option is set equal to 1 so that the number of observations that fall into each node are displayed. The under option is set equal to true to put the number of cases under each decision node in the diagram. So let's enter PRP function to visually see the tree. PRP, open the parentheses, default tree, and then type, as I said, is going to be equal to 1. The reason is because all nodes except the leaf nodes are labeled in the tree diagram, and then we will use extra is equal to 1 because the number of observations that fall into each node are going to be displayed, and under is going to be equal to true because we want to put the number of cases under each decision node in the diagram, and then control enter. Now under plus pane, now you can be able to see the tree. This is our default classification tree. The first decision node is on the sex variable, as you see on the screen, and followed by age and then income splits. Note that R represents decision trees in a slightly different format that we see in Analytics Solver. The root node provides information about how to interpret the tree. For example, the root node shows that if sex is female, then go to the left branch, otherwise go to the right branch. The subsequent decision nodes follow the same format. For example, the second decision node suggests that if age is less than 36, then go to the left branch, otherwise go to the right branch. So the next question, how are the number of splits determined in the default classification tree? The rpart function uses the complexity parameter CP to determine when to stop growing the tree. If the cost of adding another split to the tree exceeds the value of CP, then the tree growth will not continue. The default CP value for the rpart function is 0.01. However, in most cases, it's very difficult to know which CP value will produce the best performing tree beforehand. Therefore, a common practice is to grow the full tree and then prune it to a less complex tree based on the classification errors produced by a built-in cross-validation process of the rpart function. By identifying the value of CP associated with the smallest cross-validated classification error, we can create the minimum error tree. Alternatively, we can produce the best pruned tree, which is the smallest tree with an error rate that is within one standard error of the minimum error rate. Next, I am going to demonstrate the pruning process to optimize the complexity of the tree. So we first grow the full tree by using the rpart function. We set the options CP equal to 0, min split equal to 2, and min bucket equal to 1. The min split option specifies the minimum number of observations in the parent node that can be split further, and the min bucket option specifies the minimum number of observations that are allowed in the leaf node. These settings ensure that the largest possible tree will be produced. We plot the full tree using PRP function. Again, to ensure consistency of the cross-validation results, we specify a random seed of 1 using the set.seed function. So let's see, set.seed 1, and then control enter. And next we will now going to grow full tree using rpart function, and here we will use the hello is our target variable, and the remaining is going to be our predictors. Next we need to determine the data set, which is train set, and next we will use the method, which in this case it's classification tree, so we type class, and next we use CP is equal to 0, and next we will use min split 2 in order to get the full tree, and then min bucket 1 as I explained before, and then control enter. So you have the full tree created under environments pane. And in order to visualize this tree, we use the PRP function. PRP, this time we will use the full tree, and type is equal to 1, and here extra is equal to 1, under is equal to true as I explained before, and control enter. Now you see under plots pane you can see the full tree, and as you see it's very complicated. So the next step is going to be the pruning. So to identify the value of CP that is associated with the smallest cross-validated classification error, we use the print CP function to display the complexity parameter table. So let's enter print CP, and here in the parentheses is going to be full tree, and control enter. So now you see a table under console pane. Let's understand what that table means. On this table we see that we have 10 candidate trees with increasing complexity. The n split column that you see it's next to CP shows the number of splits for each tree. The number of leaf nodes for each tree can be calculated using n split plus 1. For example, the last tree has 77 splits, so it has 78 leaf nodes. The Rel Error column shows the fraction of misclassified cases for each tree relative to the fraction of misclassified cases in the root node if all cases are classified into the predominant class. As you can see, the last tree has the lowest error because it is the fully grown tree whose leaf nodes only contain cases that belong to the same class. Therefore, we do not have any misclassified cases. The X error column shows the cross-validation errors associated with each candidate tree. It's the recommended measure for identifying the tree that can potentially perform well on new datasets. As you can see from the X error column, the cross-validation errors decrease initially as the classification tree becomes more complex and then increase after a certain point. This is common and indicative of the overfitting problems with complex tree models. The second tree, which has 2 splits, has the lowest cross-validation error of 0.71824. Therefore, it's the minimum error tree. The XSTD column can be used to identify the best pruned tree, which is the smallest tree with an error that is within one standard error of the minimum error tree. In this case, no simpler tree has a cross-validation error that meets this criterion. In other words, no simpler tree has a relative cross-validation error which is less than the sum of X error plus XSTD. In this case, it is going to be the sum of 0.71824 and 0.081790. Therefore, the best pruned tree and minimum error tree are the same tree. However, in many cases, you may find that the best pruned and minimum error trees are two different trees. So we will continue in the next videos to complete the classification model. Thank you for watching this video.